Hello and welcome to this video. So we were explaining polynomials and theory of equations. We had covered up to problem number 90. So in this video we will go through 10 more problems. So without further ado, let's get started. And as always, I will say that when I'm stating the problem, you should pause the video and try to solve the problem yourself. If you cannot solve the problem yourself, only then look at the solution. So question 91 says that prove that 1 plus x to the power p plus x to the power 2p and so on up to x to the power p into p minus 1 is irreducible over z. So this problem is similar to 81, and if you want to see 81, you can say this, okay, and you can solve it like that. Okay, now we go to problem number 92. It says that solve for x, and the equation is 2p into p minus 2 into x is equal to p minus 2. So here x is equal to p minus 2 by 2p into p minus 2. Now if x is 0 or 2, then this equation becomes undefined. However, if p is equal to 0, then equation becomes 0 is equal to minus 2. Okay, if you substitute p is equal to 0, it becomes 0 is equal to minus 2, which becomes inconsistent. So no value of x will satisfy if there is satisfied and there is no solution for p is equal to 0. If p is equal to 2, then equation becomes 0 is equal to 0. Thus, every value from the domain of x will satisfy the equation. There is a typing mistake. And hence, there exist infinite number of solutions. So, if p is not equal to 0 and p is not equal to 2, then the equation is well defined and x is equal to 1 by 2p. Now, we move on to next question. It says that if x1 and x2 are non-zero roots of the equations, ax squared plus bx plus c is equal to 0 and minus x squared plus bx plus c is equal to 0 respectively, prove that a by 2 x squared plus bx plus c has a root between x1 and x2 where a is not equal to 0. So we are given two equations and two roots of those. So we substitute and the equations become x1 square plus bx1 plus c is equal to 0 and minus x2 square plus bx2 plus c is equal to 0. And f of x1 is a by 2 x1 square plus bx1 plus c, and f of x2 is equal to a by 2 x2 square plus bx2 plus c. Now if we add a by 2 x1 square to fx1, it becomes x1 square plus bx1 plus c. And if we subtract 3 by 2 ax2 square from f of x2, then it becomes minus x square plus bx2 plus c is equal to 0. So from this, we can say that fx1 and fx2 have opposite signs, and hence fx must have root between x1 and x2. Now we go and see problem 94. Problem 94 says that let p of x is equal to x square plus x plus b a quadratic polynomial in which a and b are integers. Show that there exists an integer m such that p of n into p of n plus 1 is equal to p of n for any integer n. So we let that there are two roots, x alpha and beta. So x square plus x plus b becomes x minus alpha into x minus beta. Now here alpha plus beta will be minus a and alpha beta will be b. Now we look at p of n and p of n plus 1, the product of both. So In the equation, we substitute x is equal to n and n plus 1 to obtain this relation, which is n minus alpha into n minus beta into n plus 1 minus alpha into n plus 1 minus beta. And then we solve this. And after solving, we arrive at this equation. Now, what this equation says is n square plus a plus 1 n plus b minus alpha and n square plus a plus 1 n plus b minus beta. So, this entire term we can put as m. It becomes m minus alpha into n minus beta. So, the value of m is n square plus a plus 1 into n plus b. Question 95 says that prove that if the coefficients of the quadratic equation x square plus bx plus c is equal to 0 are odd integers, then the roots of the equation cannot be rational numbers. So we see this. So it said that the numbers a, b, c are odd. Coefficients are odd. So, and it says that roots cannot be rational numbers. So we put a rational root where the GCD of PQ is 1, and then the equation becomes AP square plus BPQ plus CQ square. Now PQ both may be odd or one of them can be even also. Both cannot be even, otherwise this GCD won't be 1. And in both the cases, AP square plus BPQ plus CQ square cannot be equal to 0. But here the equation is equated to 0. Thus the equation cannot have rational roots. Now, next question says that if 1 by a plus 1 by b plus 1 by c is equal to 1 by a plus b plus c, then prove that 1 by a to the power n plus 1 by b to the power n plus 1 by c to the power n is equal to 1 by a to the power n plus b to the power n plus c to the power n for all odd n. So, you see this here. So, from the given condition, what we do is we bring 1 by c to the right hand side, and then the equation becomes a plus b into b plus c into c plus a is equal to 0. So either a is equal to minus b, or b is equal to minus c, or c is equal to minus a. Now if a is equal to minus b, then a to the power n is equal to minus b to the power n for odd n. So 1 by a to the power n is equal to minus 1 by b to the power n, which implies 1 by a to the power n plus 1 by b to the power n plus 1 by c to the power n, 1 by a to the power n plus b to the power n plus c to the power n. And similarly, you can have two other cases, that is b is equal to minus c and c is equal to minus a. Now we move on to problem 97. It says, show that a cube by a minus b into a minus c plus b cube by b minus a into b minus c plus c cube by c minus a into c minus b is equal to a plus b plus c. So let me bring the full solution. So what we have here is a cube by a minus b into a minus c is equal to minus a cube by a minus b into c minus a. We reorder the terms of a minus c to c minus a. Similarly, for b cube, we reorder the term of b minus a, and for c cube, we reorder the term c minus b. Now, from this, what we can say is a cube by a minus b into a minus c is equal to b minus c into a cube plus c minus a into b cube plus a minus b into c cube by ab into b minus c into c minus a. Once we have that, we see that right hand side is a cyclic symmetric expression in ABC in fourth degree. Writing b is equal to c, we get c minus a b cube plus a minus b c cube is equal to 0. So b minus a and hence c minus a and a minus b are factors. Since it's a fourth degree symmetric expression, a plus b plus c is also a factor. Thus we have k into a plus b plus c into a minus b into b minus a into c minus a is equal to b minus c a cube plus c minus a b cube plus a minus b into c cube. Now we put a is equal to 1, b is equal to minus 1, and c is equal to 2. We get k is equal to minus 1. and thus we have the expression here, which is valid. Now we go to question number 98. Let a1, a2 up to an be non-negative real numbers, not all zero. Prove that x power n minus a1, x to the power n minus 1, and so on up to a n minus 1, x minus n is equal to 0 has exactly one positive real root. So what we do here is we take out minus x to the power n common. So in the bracket we have minus 1 plus a1 by x plus a2 by x square and so on up to n by x to the power n. Now this is a decreasing function as x increases in the range of 0 to infinity. As x will increase, this term, the sum of terms will decrease. That means fx decreases in 0 to infinity. Yeah, this should be 0 to infinity. Hence, there exists a unique positive real number r such that f of r is equal to 1. Thus, for x is equal to r, we get that r to the power n into and so on is equal to 0. Therefore, r is the root of the given equation. Now we have problem number 99. It says, let p of x be a real polynomial function and p of x is equal to x cube plus bx cube plus cx plus d. Prove that if p of x is less than equal to 1 for all x such that mod of x less than equal to 1, then mod a plus mod b plus mod c plus mod d less than equal to 7. So, okay, let me bring the full solution. So we have the polynomial. So without loss of generality, we can assume that a and b are greater than equal to 0. So in this equation, we assume a and b are greater than equal to 0. Now, if c and d are greater than equal to 0, then mod a, mod b, mod c plus mod d is equal to p of 1. Now, p of 1 is less than equal to 1, which is less than 7. So our required condition is satisfied here. Now, if c greater than equal to 0 and d less than equal to 0, then the sum of moduli will be a plus b plus c minus d, which is equal to a plus b plus c plus d minus 2d. Now 2d is nothing but 2p0 and rest is p of 1. So we have 1 plus 2. So this would be, because d is less than 0, so the modulus will be 2. So 3 is less than 7. Now if c is less than 0 and d is greater than 0, then it would be a plus b minus c plus d. Now this we can write as 4 by 3 of p1 plus 1 by 3 of p of minus 1 minus 8 by 3 p of half plus 8 by 3 p of minus half, which will become 4 by 3 plus 1 by 3 plus 8 by 3 plus 8 by 3, which is equal to 7. So the equality is satisfied here. Okay. Now if both c and d are less than 0, then we have a plus b minus c minus d, which will be 5 by 3 p of 1 minus 4p half plus 4 by 3 p of minus half, which will be less than equal to 5 by 3 plus 4 by 3, which is equal to 7. And thus we have proven for all the conditions the required inequality. Now we come to the last problem. Problem 100. A person who left home between 4 p.m. and 5 p.m. returned between 5 p.m. and 6 p.m. and found that the hands of his watch has exactly changed places. When did he go out? So in 1 hour, the minute hand makes one complete revolution, that is, it moves through 60 divisions, and the hour hand moves through 5 divisions. Suppose when the man went out, the hour hand was x divisions ahead of the point level 12 of the dial, where 20 less than x less than 25. The reason is he went between 4 and 5, and there are 5 divisions, so 5 into 4, 20, and 5 into 5, 25. So the hour hand will be at such a division x such that it is between 20 and 25. Now suppose when Okay, when the man came back, when the man came back, the hour hand was y divisions ahead of 0 mark. So it would be 25 less than y less than 30, between 5 and 6. Given the minute hand and hour hand exchanged their places, the minute hand was at y when he went out and at x when he returned, because minute hand moves 12 times faster than hour hand. So we can write that y is equal to 12 into x minus 20 and x is equal to 12 into y minus 25. So now we have two equations and two unknowns, x and y. We solve with them and we get y as 3840 by 143. Since the man went out when the hand was at y, the man went at 3840 by 143 minutes past 4 p.m. So with this, we come to the end of this video, and I hope that you have found this video useful and informative. Now, one of the difficult problems in this entire 10 problems is this problem number 99. Figuring out these sums is not intuitive, but if you look at the formula of this, the power of x, and you see how they contribute here, then you will be able to figure out how these factors came into picture. So I hope that you have found this video useful and informative. Please subscribe to the channel and like the video. The reason why I asked for subscribing the channel and liking the video is that it increases the reach of videos to the viewers, because that's how YouTube algorithms work. So help me as well as help your peers, your co-students, and thanks a lot for watching. Enjoy.